Here's a picture of two atoms that are held together by a Lennard-Jones potential. They have almost enough energy to break them apart, but not quite, so they're still bound. The picture over here on the right shows the Lennard-Jones potential energy. This solid black line is the Lennard-Jones potential energy. There's a minimum at about -3 times 10 to the minus 21. The total energy of those two, actually we can look at all this up here. The total energy is minus 1.75 times 10 to the minus 22 joules. So that's pretty close to here, this red line right there. The atoms, I'll start this simulation in a second, but the atoms are pretty far apart right now. And pretty far apart means right around 2. 2 times sigma, which is about twice the size of an atom, the distance between the two centers. I haven't started it yet, but when I do, you'll see that the kinetic energy is very small. In fact, you can see it right up here, 10 to the minus 25. And on this kind of scale where the energies are like 10 to the minus 21, that's a really small number. So right around 0 kinetic energy, at about 2, the kinetic energy and the potential energy always add up to the total. So if the kinetic is around 0 and the total is minus 1.75, then you can see that the potential energy is also about minus 1.75 times 10 to the minus 22. So the potential energy and the total energy cross right here where the kinetic energy is 0. So I'm going to start this thing up. The potential energy has a positive slope here. Lower potential energy is smaller r, so these atoms are being pulled together. They're attracting each other. They're going to attract each other harder and harder. As they attract each other, their kinetic energy is going to go up. As they attract each other with even more force, the kinetic energy goes up even faster. And what happens is that the total energy will be constant while the potential energy is going down and the kinetic is going up as they move along this line, which is r, the distance between them. So as they get closer together, we'll be moving along this graph to the left, and then they'll come back and move farther apart again. Let me just start this and you'll see how it goes. If you look up here at the kinetic energy, you see that it's rising. This thing is moving to the left. They're going closer and closer together. Kinetic energy gets large. It gets small again when they hit, and then it bounces back apart. And then they come all the way apart again. So I'm going to go through this. I'll let it bounce once more. You can see that they're moving slowly. Kinetic energy is small. They start to move faster and faster, so kinetic energy is going up. And then they get near each other, they stop right there, and then the kinetic energy comes back again as they spring apart, and then it goes back down again as they get very far apart. And we can look up these numbers. I'm just going to stop this and show you where we are. We started out with potential energy and total energy about equal. That's right there. As we move these two closer together, so I'm moving to the left along this line, this horizontal line where r measures the distance between them. As we move them closer together, the potential energy goes down, the kinetic goes up, and you can see that up here in these numbers. Potential energy is going to go down. It starts at minus 10 to the 22, 1.76 times 10 to the minus 22. It'll go down when I bring them closer together. You can see it's already going down right now. The potential energy is minus 1.65 times 10 to the minus 21. Kinetic has gone up. Now the potential, they haven't exactly bounced back yet. This is about where the potential energy is a minimum. And that's about there, 1.12 or something. The potential energy is a minimum at about -3. You can see it's minus 2.85 times 10 minus 21. Kinetic energy is a maximum here. Close to 3, not quite. About 2.68 times 10 minus 21. If I take this just a tiny bit farther, so the atoms get a little closer together, that's as close as they get together right there. The kinetic energy has dropped to 5 times 10 to the minus 22, so that's about there. Kinetic energy is not quite 0, it's headed towards 0, but I don't think that that 0 is exactly in my simulation here. I didn't screen capture the exact 0. The potential energy it's negative 6 times 10 to the minus 22. That's about right here. So the kinetic plus the potential still add up to this red line. The total energy is still minus 1.75. If I go just a little bit farther apart, the kinetic comes back again. I guess the maximum kinetic that I actually got on this simulation is 2.66 times 10 to the minus 21. So the kinetic has come back as they spring apart. Kinetic energy comes back again. Potential energy is minus 2.84. It drops back down again. Still the sum of the potential and the kinetic adds up to the total. I'm just going to let it go. And you can watch that happen. I'll let the whole thing run out. And in replaying this, if you want to stop the simulation at various points and check the energies, you can see that the kinetic energy maps out that dotted line there, and the potential energy maps out the solid line in between those two turning points. The turning points are 2 for the maximum, like right where they are right now, are around 2 sigma apart, and the minimum is around 1 sigma. And that's it.